So the title of this clip is the divergence, and let's first define what it is. So we have a vector field, f of x, y, z, which is p of x, y, z. This is a scalar function in the I component plus q of x, y, z. In the j component plus r of x, y, z in the k component. So this is a three-dimensional vector field. And the divergence is defined as follows. So it's denoted, so this is a definition. The divergence of f, and it's written div f, is by definition the derivative of p with respect to x. P is a function of three variable. I take its partial with respect to x, plus the derivative of q with respect to y, plus the derivative of r with respect to z. This is weird. This is weird. Why would I want to do that? Why would I want to take p, ignore its derivatives with respect to y and z, and only look at its derivative with respect to x? For q, only look at its derivative with respect to y, and for r, only look at its derivative with respect to z. Remember that these three functions are functions of three variables. These three partial derivatives are also functions of three variables, and I'm adding them. So this is a scalar function of three variables. Let's emphasize that. This is a scalar function. So the divergence of a vector field is a scalar function of three variables. Okay, is that clear? Okay. And some more notation. This symbol, which is called nabla, what we used for the gradient, this symbol, what was it? It was, in a sense, it was the vector whose components were the partial derivative with respect to x in the I coordinate plus the partial derivative with respect to y in the j coordinate plus the partial derivative with respect to z in the k coordinate. This was this vector. Okay, so maybe I should write it like this. Okay, and this is kind of abusing notation. So this is a remark. This is a remark. This is abusing notation. It's not a vector. It doesn't have components. A vector should have honest components, 3, 7, and pi. These are just symbols, okay? But this is what this operator, that's the correct word to use for it, this is what this operator does. This is how it operates on a function. So if you take the gradient of a scalar function f, what you get is the derivative. You get a vector df to dx in the I component, df to dy in the j component, or since I wrote it like this, and df to dz in the k component. Do you see why it makes sense to think of this operator, this derivation operator, which we called nabla, serving as the gradient? It does precisely that. Okay, you plug in f and you get this. Do you agree? Now, this thing is also denoted. Another way to denote this is take this operator and do dot f. This is alternative notation for the same thing. And why does that make sense? Think of this operator. It has three components. Dot it with f, p, q, r. So what do you get? You get this times p plus this times q plus this times r. Okay? So this notation, which I'm going to use, I'm usually going to use this notation rather than the div f notation, is really suggestive. It tells you how, it reminds you, if you remember what the nabla operator is, it reminds you exactly what this thing is. Okay, clear? Is this clear? Okay, so this is the divergence. Maybe it now makes a bit more sense. Why are we looking specifically at these three partial derivatives? But it's still mysterious. And what I want to do now, there are various ways of introducing the divergence, but what I want to do now is to show you the kind of the physics behind it. What does this thing really do? And that's actually going to lead to the theorem called the divergence theorem that's going to come up next, which is also called Gauss's theorem. So this is the divergence. Let's see what it means. Why are we looking at this sort of thing? So here's the physical meaning, the physical interpretation, or at least an informal way of thinking of it. So suppose we have, here's the XYZ coordinate system. I'm going to draw it a bit bigger. X, Y, and Z. And suppose we have a little box sitting in the XYZ coordinate system, and all its sides are parallel to the axes. So we have a little box that looks like this. Here's a little box. Okay? And it's parallel to the axes, and we're going to assume that it's sitting here. Let's not use black, that's the box itself. Let's take a different color here, a couple of them. So it's sitting here. The value here, let's say, is y, and the value here is y plus some delta y. So the length of this side is precisely delta y. And likewise in the x and in the z. So the length of this thing is going to be delta z. It's going to be sitting between z and z plus delta z. And the length of this thing is going to be delta x, sitting between x and x plus delta x. Is that clear? Okay. Now, I want to know, suppose, so this box is a surface now. It's going to be a little surface, a closed surface, It's closed. It has all 6 sides. And suppose that all the normals are pointing outwards. And let's restrict our attention to these 2 sides of the box. This side, with the normal pointing this way, and this side back here, you should see that this is in the back. This goes in front. This back side here, whose normal is pointing in this direction. Okay? And suppose there's a field, F equals PQR. And the field is defined everywhere. I can add little arrows representing the field. And I want to know what is the flux of the field coming out of the box. What is the flux of the field coming out of the box? So what is the flux of the field coming out of just this side here? So remember our discussion of fluxes in terms of water and nets. So here's this side here. It's parallel to the xz plane. And whatever the direction of the field, whatever the arrow is, only the q component of the field is going to contribute to the flux through this side of the box. Do you agree? Everybody? Only the q component of the field is the component in the direction of the normal, right? We had to in order to calculate the flux, we had to take the direction of f in the direction of the normal. So this is n. So only the q component contributes to the flux here. Over here on this side, also only the q component contributes, but with a minus sign. So minus q contributes to the outgoing flux on this side here. Okay, so let's write it. Let's call this side, I'm going to call B, and this side I'm going to call A. So flux out of B, sorry, out of, which one did, oops, made a mistake, A and B. This is A and this is B. The flux out of A, again, we're thinking of a little tiny box. We're going to add up all these little boxes into a big surface in a moment, but little tiny box. We're assuming that the field is constant on this side. So the flux out of A is approximately minus q evaluated at, let's say, this point, doesn't matter, x, y, z, times the size of A, right? The area of A, which is delta x times delta z. This is the flux out of A. Minus because I'm thinking of the normal pointing this way, so the flux out is minus the flux going in this direction, in the positive direction. Good? Okay. The flux out of B is approximately, there's not going to be a minus, it's just the regular positive direction, so it's q, not at x, y, z, which is this point, but at x, y plus delta y, z. X, y plus delta y, z, times the area of B, and the area of B is still delta x times delta z. Do you agree? Good? Clear? Okay. So combined, add these two up, we get, well, we're going to add it here. What we get is q of x, y plus delta y, z, minus q at x, y, z. And I'm going to divide, so let's write the total on A and B. I'm going to divide it by delta y, something I can always do providing I multiply it back by delta y, and I get delta x, delta y, which is what I multiplied by, delta z. Clear? So the total flux out of A and B is this expression. What is this expression? What does it look like? Q is a function of 3 variables. This is the little increment in the y component. So what is this thing? Exactly. This is the derivative of Q with respect to y. So this equals, so let's write it here, total flux. I'm going to need more space, so let's continue here. Total flux out of A and B is the derivative of Q with respect to y, the derivative of Q with respect to y, times delta x, delta y, delta z. Now, you can do the exact same arguments, the exact same analysis, and look at the two faces of the box, one sitting here in the front and the one sitting there in the back. And for those, the only component contributing to the flux is going to be the p component of the field, the component in the direction of x. And then you can do the same analysis for the top and the bottom. For those, the only component of the field contributing to the flux is going to be the r component of the field. Okay? And what you're going to get is that the total flux out of the box, the little box, is dp to dx plus dq to dy plus dr to dz times delta x, delta y, delta z. Delta z. Okay? So what we calculated is the contribution of Q, which only contributes to those two sides, and similar arguments would get you this. Now, so this is the total flux out of the box. Now suppose you have a big surface, and you want to know what is the total flux out of the surface. Okay? So the total flux out of the surface is going to be, break it up into these little boxes. Each box contributes this, and then add them up. Okay? So, and this is by no means a proof of anything. This is just the idea. The idea. So, for a, what's important here that it's a closed bounded surface, not just any surface. So for a closed bounded surface, a closed bounded, it's not the, it's the domain. Let's write for a closed bounded solid V, for a closed bounded V, the total flux coming out of its surface, coming out of it, for a closed bounded V, the flux, the outgoing flux, the outgoing flux is sum all of these over all these little boxes, and in the limit, when you refine the summation, what you're going to get is a triple integral of this function, which is the divergence of f. Take a quick look at this board. That's how we defined the divergence of f, right? So it's the triple integral over the entire volume V of the divergence of f dx, dy, dz. Okay, so this is the bottom line. This is the physical interpretation of the divergence. If you integrate the divergence of a field over a volume, over a solid, what you get is the flux coming out of the solid, providing that you think of the normal pointing outwards at every point. Okay? And this is precisely what Gauss's theorem is going to say, but that's going to be in the next slip. We're going to say that, well, we'll say it in the next slip. This is going to be Gauss's theorem. Okay? Questions? Is this clear? Everybody good? Yeah, about this? This is notation. Writing this, it's not the gradient. The gradient is when we apply this operator to a scalar function. Then it's the gradient. Then it's precisely this thing. This is an operator which now has another meaning. It's going to have a third meaning when we talk about Stokes' theorem. Okay, so this operator, which just takes the derivative of whatever you're looking at with respect to x in the I component, with respect to y in the j component, and with respect to z at the k component, when you apply it to a scalar function, what you get is called the gradient. It's this thing. When you apply it in using the dot, when you dot it with a vector field, and this is just notation, what you're doing is you're taking the derivative with respect to x dot the first component of the field, p. So you get dp to dx, plus the derivative with respect to y, that's the j component of this operator, dot q. So you get dq to dy. This is what's called abusive notation. We're really, I'm not inventing this term. It's called abusive notation in a sense. So this is not a vector field. Usually we dot vector fields. This is not a vector field. This is a vector field. This is an operator. Okay, it operates on the vector field. In what way? In this way. And this is just a short way of expressing it. Okay, good. Okay, so remember, the divergence of a field measures the outgoing flux when you integrate over the entire body that you're interested in the outgoing flux for. Coming up next, the divergence theorem or Gauss's theorem.